Okay. Okay. So hello everyone. In this webinar, we are going to cover the basic concepts about big data technology, including the key components of Hadoop, which are Hadoop Distributed File Systems, that is HDFS, and MapReduce. So first things first, big data, which is commonly described using three terms: volume, velocity, and variety. It is all about the data which is huge and which is much larger than the normal capacity of traditional databases. Apache Hadoop provides one possible way to implement big data. Hadoop was originally created by Doug Guttin and Mike Cafarella in 2005, and it was taken up as the top-level Apache project in December 2011. The Apache Hadoop software library is a framework that allows for the distributed processing of large data sets across clusters of computers using simple programming model. It is designed to scale, which means it can scale from single servers to thousands of machines, each of which offers local computation and storage. Hadoop comprises of a library which itself is designed to detect and handle failures at the application layer. Thus, it delivers a highly available service on top of the clusters of computers, each of which may be prone to failures. It provides a system of reliability without having to depend on any such requirement from the underlying hardware. That means even if the hardware you are using is not reliable, the overall Hadoop system will still remain reliable. Here is the high-level architecture diagram of Hadoop. Here, the elements or the boxes in red shows the core components of Hadoop, while all the other colors shows additional components. The core components comprises of the distributed storage framework, which stores all the data, and distributed processing framework, which processes the data. The other supporting frameworks are the integration frameworks, which integrates Hadoop data with other external data sources like RDBMS. Management frameworks, which is responsible for overall management and maintenance of Hadoop. Development frameworks for writing the code in high-level language. Business intelligence and reporting framework. This includes third-party tools and applications for business intelligence and reporting. Here is a detailed drill-down view of the Hadoop architecture. The core components, which are shown in red color, the distributed storage framework. Hadoop uses Hadoop Distributed File System, or HDFS, to store data. The distributed processing framework, Hadoop uses MapReduce and Yarn to split up its tasks across multiple participating machines. We'll be taking them in detail very soon. The other supporting frameworks, integration framework is shown in green color. It includes various tools and utilities like Sqoop and Flume to integrate Hadoop with other common systems like RDBMS. Management frameworks are shown in gray color. It includes various frameworks for overall management and administration of Hadoop, like Zookeeper, Ambari, OZ, and other security and governance related components. Development frameworks are shown in blue color, which denotes the high-level languages like Pig and Hive. These are used to query the data which is stored in Hadoop. Business intelligence and reporting frameworks are shown in yellow color. This mostly includes third-party applications like SAS, MicroStrategy, Microsoft Excel, or Splunk, which enables reporting capabilities with Hadoop. Other frameworks shown in dark blue color includes NoSQL databases and additional application frameworks like streaming, graph, online, which are still in experimental phases. Before proceeding further, let us get familiar with some of the commonly used terminologies when talking about big data. Node. A node is any system or machine deployed on a commodity hardware or a high-end machine which are having some processing capabilities. Rack. A rack is a collection of nodes physically grouped into single geographical locations. All the nodes within a rack usually share a common infrastructure like power, cables, network devices, etc. Cluster. Collection of multiple racks which may be placed across entirely different geographical locations. For instance, a single cluster of Yahoo can have multiple racks, one of which may be placed in New York while other is kept in Mumbai. This also forms the core of the distributed file system storage, where a single file is stored and distributed across several systems based on the block size. Hadoop Distributed File System, or HDFS, works on the principles of distributed file system. Now let's dig a bit deeper into the core components of the Apache Hadoop. On the storage side, we have Hadoop HDFS, or Hadoop Distributed File Systems. In this, the storage data is distributed across nodes, which may be present at physically distinct locations. The nodes are natively redundant in nature, which means even if any node fails, the system will automatically take care and make data available. Within all the storage nodes, some nodes track the location of the data, that is the metadata. Such nodes are called name nodes. The other nodes hold the actual data, which are called data nodes. On the processing side, we have Hadoop MapReduce. In this, some nodes schedule and monitor the data processing nodes, which are called job trackers. The other nodes perform the actual processing of data, which are called task trackers. Every new task is split into smaller subtasks. This split is done in such manner that the node nearest to the actual data receives the job of processing that data. When the task trackers have completed their tasks, job tracker gets the assembled results which are sent back to the client. We'll see all these concepts in the coming slides. HDFS basics. HDFS follows distributed file system, which enables it to hold data of all sizes and variety. It can store traditionally structured data in form of tables, and also it can store unstructured data in form of log files of large sized blobs stored across different nodes. This makes it possible to hold enormous volumes and variety of data. HDFS is based on Google file system, which follows master-slave architecture. There is usually one master node called name node, which keeps track of all the data stored across all the other nodes. The client machine always interacts with the name node, which has all the details about the data which is stored across the entire Hadoop cluster. HDFS is the primary storage system used by all Hadoop applications. The key characteristics of HDFS are as follows. It is scalable. It adopts scale-out architecture, which means any number of new nodes can be added to the cluster at any time. It is efficient. It supports parallel reading and processing of data, which is often stored across multiple nodes. It is fast. It provides high throughput across the application data, which means processing will be faster. It offers load balancing. Data is distributed and stored intelligently by the Hadoop itself. This provides maximum efficiency and utilization without any intervention of the end users. It is fault tolerant. HDFS can recover from the failures automatically. If any node fails, the data can be retrieved from the other replication nodes. It also offers data integrity. To ensure data integrity, Hadoop uses checksum verification method for all the data written to and read from the HDFS. It can be deployed on low-cost hardware, as it is designed to be deployed on the low-cost hardware only. It stores very large files across machines in large clusters. Here is a quick comparison between Hadoop HDFS and traditional NFS-based file systems. First of all, redundancy. Hadoop HDFS provides redundancy across physical switches and networks, which helps ensure that data is always available. While in NFS, no built-in redundancy is available, and some additional redundancy mechanism is required externally. Block size. Hadoop HDFS deals with large size blocks, which are around 64 to 128 megabits in size, whereas in NFS, we only have 4 to 8 kilobytes of block size. Optimal use cases. Hadoop HDFS works best when we have read operations for huge size files ranging from few hundreds of megabits to gigabits or even more. Whereas NFS is suitable for applications which need randomly to arbitrary positions in file, which are basically for smaller size files. Management tools. The entire Hadoop can be managed using web server based portals, while NFS had command line prompt based tools for management related activities. Storing huge files. As you can see on the screen, Hadoop HDFS can store files of size hundreds of GBs by splitting it across different nodes based on the availability of size on the node. So a single file can be split across 2 or more nodes. While in NFS, this mechanism is not easy to implement. So one straight advantage of using HDFS is that you will not get the error disk size insufficient, which you might have seen in ordinary NFS-based systems. MapReduce. MapReduce is the processing framework first developed by Google for processing large datasets. A MapReduce job usually performs the following steps. In the map part, the input task is split into independent subtasks based on the number of nodes where separate map tasks can run. Each subtask is then directed to perform the required processing on the smaller chunks of data, which are completely independently processed. Once the processing of each independent node is completed, the Hadoop framework sorts the output of the maps, which are then sent as input to the reduced tasks. The reduced task summarizes the results from all the map tasks and sends back the output to the client. In this manner, for any task that might take up to 3 hours on ordinary systems, you can split that task into 3 parts and process them in parallel, thereby completing the entire processing in just 1 hour. Let us see in details basic concept of MapReduce, that is, how MapReduce works. First, you need to submit a task to the Hadoop head node for processing, either to the Hadoop application programming interface or via an interactive console. The head node, which is called name node, then figures out how the data is partitioned. Then, based on the partitions, it defines the mapper and reducer tasks. So, for example, if the data to be processed is split across 5 different nodes, then Hadoop system will automatically split the entire processing into 5 different subtasks, and each of the subtasks will be performed on each of the data node independently. For this example, we are provided with a list of keywords and a bulk of content in form of independent files. We need to count the occurrence of each of these keywords in the entire set of content. As you can see, that there are repeating data values for the region ID column. The head node can use this as a potential partition values to parallelize the task. We will then count the number of occurrences of the keywords. This example, we are going to start with large files or set of files that contains messages. Each message may contain 0 or more occurrences of specified keyword in the list, including errors, issues, problems, concerns, warnings, contexts. These are some of the keywords which are available in the file. These are actually the log files, the data which we are taking as an example. This data is basically from log files, which keeps track of all the transactions happening to a website. So for any particular system, if on a server, a website is hosted and it is keeping a track of all the interactions that are made to the website, then these will be the some things or some format you will find in the log files for that particular server. Now, the common problem faced when processing or analyzing those records is that those records are huge in size, extending to some GBs or TBs, and it is very difficult to identify and analyze the number of errors or issues that were faced or happened on that website. Ideally, if all the data is stored on the relational database, first of all the log files need to be merged or converted to appropriate RDBMS format, and then those will be processed. But even after converting into the RDBMS format, size of the data is huge, so processing will definitely take some time. Instead of moving or converting them to the RDBMS format, what a user can do is you can simply use those log files directly into the Hadoop system. In this example, we'll try to process sample data which will contain the keywords like error, issues, problems, etc., and count the number of occurrences for each of the keywords. In actual processing, instead of counting, many different actions or tasks can be performed. Ideally, if you are familiar with the T-SQL, the MapReduce task that we are going to see is equivalent to executing the query you see over here. It is selecting the keywords and the sum of occurrences from all the messages, which are basically grouped by the keywords. Now let's see how Hadoop processes the map program. First, the task manager distributes portions of master dataset to all the member nodes based on the partition value. In our example, the partition value can be region ID. So if you are talking about some website, then for that website, the partition can be based on the location from where the users have accessed the website. Region ID 10 may be all the users from Asia Pacific. Region ID 20 can be all the users from Europe. In that manner, the huge amount of data which the website had is now split into smaller subsections. Each member node takes the role of a mapper. In our example, we have 3 mappers, M1, M2, M3, and the actual number can be Mn. So there will be n number of mapper tasks, which will ideally be based on the number of regions in which the data is divided. The mapper output is cached into a temporary table that is used in next phase. The mappers will do the calculation in each of the mapper node. The data which is present across that node will be processed. So for example, the entire data in the European region will be processed by one single node. In similar fashion, all the nodes across all the different regions will process their corresponding data. Once that data is processed, it is pushed to the reducers for next steps. We will see how that happens. So each of the mapper performs its own tasks. So we see in region 10, the total number of occurrences of the word error was 19, issues was 23, and problem was 22. In similar manner, all the different mapper nodes have processed and counted the occurrences of the keywords within their region. The red color shows the number of occurrences of keyword error, possibly in European region. In this manner, the entire task of processing bulk amount of data is now split into smaller subtasks. The mapper then pushes the result of the count per keyword to the reducers. The reducer then processes the output from the mappers. The tasks assigned to each of the reducer is shuffled from the mappers. So, for example, the reducer 1 will get a task of collecting and counting the number of occurrences for the word error. In our example, the reducer 1 gets the outcome of number of count of the word error from mapper 1, mapper 2, and all the other mappers. So reducer 1 will be responsible for only the single keyword error. It will fetch the results from each of the mapper tasks, and then it will do the processing. This kind of split of tasks is especially helpful when the tasks involves scanning each of the records one by one. In similar manner, reducer 2 gets the keyword issues, 3 gets the keyword problem, 4 gets the keyword concern, and so on. In actual practice, the number of reducers is also can be restricted based on the end user requirement. So it was also possible to compile the entire results using a single reducer, or possibly we can have just only 2 reducers and all the keywords could be split accordingly. The last phase, the reducer finishes up carrying out their operations in parallel. You can see that we have the totals for each of the keywords that each reducer computed. The reducer 1 computed the count for occurrence of the word error. In similar fashion, each of the reducer completed their own processing, and since this was done all in parallel, the computation becomes very much faster. The data summary unit then takes the results from the reducer to create a temporary table for the results. The temporary table is sent to the desired output stream format, where you can apply a statistical model to the results, or generate graphs or charts, or pipe the results into another MapReduce programs. So for example, based on the number of keywords, if you want to initiate some other processes, like if the count of error increases from a bare minimum level, say 50 errors, then automatically some action should initiate and the website should be looked into. And all this processing, since it is done in parallel, it will happen in almost real time, and thus, in case any error are occurring on any website in real time, it can be located very easily. The temporary table is sent to the desired output stream format. Now you should have a better understanding of how overall MapReduce process works. This is just an example of the concept level explanation. In actual practice, when all these things happen, the mapper nodes and the reducer nodes are the actual job trackers and task trackers which are installed across the cluster. Within the Hadoop cluster, where we have several nodes, few nodes take the role of mapper, while the others take part of reducer. Now let us have a quick comparison between Hadoop, traditional SQL-based systems, and massively parallel processing systems or MPC systems. First of all, scalability. Hadoop possesses scale-out capabilities as we have already discussed, and similar capabilities are there with MPP systems as well. So if you want to increase the number of nodes from 100 to 200 Hadoop and MPP systems, this will be possible easily. But in the traditional SQL systems, we need to scale up. So even if you want to increase the capacity by one node, it will increase a very complex process. Data models. Hadoop adopts the key value pair based data model, which makes it much flexible and faster than both SQL and MPC systems. Traditional SQL-based systems usually follow relational databases tables, and the same is followed by MPP systems as well. For programming model, Hadoop has a functional programming model which includes the map and the reduce functions. So for processing any task in MapReduce in Hadoop, map and reduce functions need to be written. This makes it stand different from the other traditional SQL-based systems and MPC systems, which are mostly declarative queries. So for example, when we say T-SQL, the select query, these are all declarative queries, whereas in Hadoop, we have functional programming. For processing, Hadoop is optimized for offline batch processing tasks for huge sized files extending to GBs and TBs. And as we already saw, the reason for this, Hadoop is the only system capable of splitting of single file across multiple nodes. Unless before Hadoop, it was really pretty hard to store one single file across multiple systems and then process the same file across those nodes, computing the results and getting the outcome in so easy steps. The traditional SQL systems and the MPP systems are efficient with online transaction processing tasks and applications. These were the basic concepts regarding map and reduce. The next steps that are covered in this module are about Hadoop architecture, which will be taken in depth during the actual training. For now, maybe if anyone has any questions, or maybe we can open the deck for questions now. And if anyone has any questions, we are here to answer.
Okay, thanks, Vishal. I'm going to take it over from here. So let's see. Thanks, Vishal, for sharing your knowledge on Hadoop, on the big data technology stack, Hadoop, and so on and so forth. At this time, does anybody have any questions? If you have any question, please go ahead and unmute yourself and go ahead and ask the question. Okay, does anybody have any questions for Vishal or Badal regarding big data? Anything regarding big data?
Okay, so till the time everyone is thinking about the data or those things, maybe I can share some interesting things about big data. If we have some time. Manish, do we have some time?
Yeah, okay. Do you want me to give you the control back so you can share your screen?
Yeah, maybe please.
Okay, all right. Okay, so I'll keep the floor open. I'm just handing it back to Vishal. So in case anybody has any questions. Vishal,
sure.
share your screen.
Yeah. In the meantime, if anyone has any questions, you are most welcome to interrupt me anytime in the middle. Right. Until then, I'll focus a bit more on the Hadoop architecture. So I hope the basic concepts regarding the Hadoop file system and the processing part are clear. For storage, Hadoop uses HDFS, which is the Hadoop distributed file system. And for processing, when Hadoop was originally developed, it had MapReduce concept. But you might have all heard also about Yarn, which is an updated or upgraded version of MapReduce. Originally, MapReduce was just a basic concept which we had discussed already right now, but which had many bottlenecks. For instance, when the cluster was given any task, all the nodes which are involved in map and reduce tasks were allocated their responsibilities, but at the similar duration, all the other nodes which were present in the cluster, even if those were idle, those could not be utilized. This was one of the major bottlenecks with the traditional MapReduce part. So to overcome this and several other bottlenecks, Apache Hadoop Foundation decided to come up with another version which is known as Yarn. Yarn is a very latest version of distributed processing, which most of the tutorials won't cover. But in this tutorial, we will be covering the basic concepts of MapReduce as well as Yarn, including the details about how each and every node acts and how the processing actually works across MapReduce and how it differs in Yarn. Besides that, also we have the BI layer. In the BI layer, most of us would be familiar with Excel. Microsoft provides inbuilt, or maybe I should say, very close architecture to interact with Hadoop. It has its own drivers, the ODBC drivers, to fetch data directly from Hadoop systems and which can be accessed in Excel. So in the tutorials, we will be also covering the ways to export and explore the Apache Hadoop data into Excel files and to analyze that data. These are the few of the things which we are going to cover.
Okay.
Manish, would you like to add anything here?
Yeah, so we have a lot more. So we have a big data training coming up. Thanks, Vishal, where we'll be going into details. So if anybody is interested in knowing more about this, then you know how to get in touch with me. I will share our contact information as well. I'm going to take the control back from you, Vishal. And so you can send us an email at info@omni, if you can see my screen, info@omni212.com. We are actually based out of Bellevue, Washington. We have office in downtown Bellevue, but we also have a training location, a classroom training in Redmond. So we'll be doing in the upcoming weeks and months online as well as classroom big data training. So you can also Google us or Bing us, Omni212. We are right here. And my name is again Manish Roy. I will go ahead and include my personal email address as well, which is manish.roy@omni212.com, and you can send me email. Okay.